Hi viewers, this is Sriram, lecturer in KBN College. Today I am dealing the chapter 3, that is block ciphers and the data encryption standard. So in this chapter we will see various block ciphers. So the procedure followed in the block cipher and the very popular encryption algorithm in the symmetric, that is a data encryption standard. So you will go into the details of these data encryption standard and the block ciphers. Now let us see the modern block ciphers. The first concept is the modern block ciphers. So nowadays most of the symmetric algorithms are using these block ciphers because block ciphers create a very complex ciphertext. Okay, that's the reason why most of the modern cryptographic algorithms are using this block cipher. So it provides both the confidentiality and authentication services. So you can provide both the confidentiality and authentication services by using these block ciphers. So in this chapter we provide more focus on the DES, that is a data encryption standard algorithm, which is very popular algorithm. So we will illustrate also the block cipher design principles, how the design is being created for the block ciphers. We are having two types of, as I already discussed in the chapter 2, we can see the cryptography in two ways. We can generate the cryptographic algorithms in two ways, that is in block cipher and the stream cipher. So if you see the block cipher, we will divide the plain text into a fixed size blocks of any size. So we will divide the original plain text into a fixed size blocks so that it becomes easier for us to encrypt those blocks. Instead of encrypting the whole message, the plain text one at a time, if you divide the plain text into a fixed size blocks, you can encrypt those boxes separately and you can decrypt those boxes separately. That becomes easier. And you can also create a very complex ciphertext by doing so. So usually we use a fixed size like 64-bit block. So because by choosing the 64-bit block, it is satisfactory to create a complex ciphertext. And we are also having the stream cipher. In the stream cipher, we encrypt the message bit by bit or byte by byte, and the decryption is also done bit by bit and byte by byte. So it is not become very popular. So most of the current symmetric encryption ciphers are using this block ciphers only. We are having a very range of applications, broader range of applications which uses the block cipher. So this is about the block cipher and the stream cipher. You can see the block cipher principles. So most of the symmetric block ciphers are based on the Feistel cipher structure. There is a very popular cipher structure, introduced by the Feistel, that is the Feistel cipher structure. So he provided a very complex cipher structure. Okay, so we need to decrypt. So that structure should also create the procedure how to decrypt. Instead of not only generating the ciphertext, you should also provide a technique how to decrypt the ciphertext to recover the plain text. Okay, so block ciphers looks like an extremely large substitutions. If you see these block ciphers, we use a very complex substitution. Means we make many substitutions here in the block cipher. So we use many substitutions in this block cipher. So the cryptanalysis is also very tough because the cryptanalyst has to use 2 power 64 entries for a 64-bit block. So which is a very complex task for a cryptanalyst to generate 2 power 64 entries. So instead of creating a smaller building blocks, in the sense we are saying that we are dividing the plain text into blocks. So for generating an encryption, if you use by smaller building blocks, means simple substitution and simple transposition technique, it becomes very complex for us, for the person who are encrypting, very complex. But if you use a product cipher, so it becomes easier for the person who encrypts, so it becomes easier and it generates a very powerful ciphertext. Okay, so these are the design principles, cryptographic block cipher principles. If you see the ideal block cipher, so the ideal block size is 64, but for the time being we are showing the 4-bit block cipher. So how the 4-bit block cipher will works? So here for 4-bit block ciphers you have to choose 2 power 4, that is 16 entries, so 0 to 15. So here for each and every byte they can choose any of the numbers in the 0 to 15. So the cryptanalyst cannot identify, so first byte is chosen which bit, second byte chosen which bit, so it becomes very complex. So for 4-bit only this is creating such a complex. So for 2 power 64 bits, for 64-bit block it is a very much more complex. Next one is Claude-Shannon and substitution permutation ciphers. So we use here the SP networks, in the sense substitution box and permutation box network, which is introduced by Claude-Shannon in the year 1949. So most of the modern block ciphers use these SP networks only. So combination of substitutions and permutations, they are popularly called as S box and P box. So in the DES also, data encryption standard also, we use these substitution boxes and permutation. The combination of these substitution box and permutation box, that becomes a complex ciphertext. And by using this S box and P box, we can create confusion and diffusion to the our message plain text, and also we can create to the key. Now let us see what is the confusion and the diffusion. So a ciphertext need to be completely obscure the statistical procedures. So what is an ideal ciphertext is, it has to create it has to obscure the completely statistical properties of it. You shouldn't see any of the things related to the plain text. It should completely obscure the elements of the plain text and generates a very complex ciphertext. So that is the ideal ciphertext. We can generate the type of ciphertext by using one-time pad, which is one of the substitution technique. But using one-time pad is very complex, because every time you need to choose a different key. But a very practical thing we can do is using the Shannon suggested SP and SP networks. So using the SP networks you can create such complex ciphertext. If you see diffusion, dissipates statistical structure of plain text over bulk of ciphertext. So just like spreading the elements of the plain text, just you spread the seeds in a land, just to spread seeds in a land, you will just spread the letters of the plain text on the paper and generate a ciphertext. So it becomes very complex ciphertext. That is called the diffusion. And confusion, so it will create this the relationship between the key and the ciphertext is very complex. Means, in the sense, you cannot identify the key by looking at the ciphertext. So such a complex ciphertext if you generate, that is a confusion. So you can create confusion and diffusion by using these SP networks. Next concept is the Feistel cipher structure. So the next topic is the Feistel cipher structure. So this is very popular cipher structure which is used in many cryptographic algorithms. So this cipher structure is devised by the author Horst Feistel. He is a scientist who invented this Feistel cipher. So it is based on the concept of invertible product ciphers. What this Feistel cipher means, in this cipher structure they use the product ciphers which is invertible. You can do even the inverse process of this product cipher. Means you can do encryption, and in the same way you can do decryption in an reversible way. No need to use separate algorithms for encryption, separate algorithm for decryption. So that is the concept, the Feistel cipher structure. So in this Feistel cipher structure, what you will do is you will divide the input block, you will divide the plain text block into two halves, two equal halves. Okay, so by after dividing that, you will process multiple rounds for having a better complexity. In the sense, you do substitutions and permutations not one time. You will do that for number of times. For example, 16 rounds or 32 rounds or 48, like this. There are different algorithms. We will use different number of rounds. So this Feistel cipher structure uses this number of rounds, so that the cipher structure becomes very much complex, and it performs a substitution on the left data half based on the round function of the right half and subkey. In the sense, so the substitution is done in the Feistel cipher to the left hand part of the because you divided the plain text into two parts, plain text block into two parts, left part and the right part. Left half is directly swapped to right half for the next round, but whereas for the right half it will generate a function that is called the round function with the input of the right half, and it is exclusive or with the left half data, and it also uses the key. It is a round key. For each round use a subkey, that is called a subkey. So with the combination of subkey and the right half data, you generate a function that is a round function, and that is exclusive OR with the left hand data. So after combining that data is swapped to the right side to the next round. So this is the this process is followed for 16 rounds, whatever may be the specified number of rounds here. The same process is repeated. So by doing this process repeatedly, the cipher text becomes very complex based on the round function of right half and subkey. And you have used permutation swapping halves. So after the round function is calculated for the left hand of data, so both the halves will be swapped using the permutation. Left half part is swapped to the right half part, and right half part is swapped to the left hand part for the next round. Okay, so it implements the Shannon's SP network, that is a substitution and permutation network concept. So this whole process in different rounds, they use various substitutions and various permutations. So you will see, you can understand when you see a diagram in depth. See, let us see the diagram first. This is a Feistel cipher structure diagram. So in this, the plain text, so it is a one block of plain text that is divided into two halves. It is, for example, consider it is a 2W, it is W bits and W bits. This is the left hand part, that is L0. This is R0, right hand part. So this right hand part is directly swapped to left hand part for the next round. That is R0 is swapped to L1 directly without having any modification. Directly the input is swapped by process of permutation. But whereas for the left hand data, that is L0, a round function. Here this is a function, this is a round function. So a round function is calculated using the right half data. So you can see the input from the right half data and also from the sub key, that is k0. So this is because this is a round one, k0 is the sub key for the first round. So it takes two inputs on the sub key and from the right half data part and generates a function, and that function result is given as an output input to the left hand part data, and do exclusive OR, and then this data, the output generated, is swapped to the right half part, then it becomes R1, and the right hand part directly swapped to left hand, this is L1, and the same process is repeated for 16 rounds. If you see here this is the Ki and then Kn. So finally you will see Ln plus 1, Kn plus 1, and the final output is the ciphertext. So by doing this process repeatedly for 16 number of times, you will get the ciphertext. So this is a process followed in the Feistel cipher structure. Now let us see the Feistel cipher design elements. So what are the things which you use in this design of the Feistel cipher? If you see the block size is usually 64 bits or 128 bits or even 256 bits. If you use the block size, increasing number of block size, the complexity becomes bigger, but the cipher performance gets low. So you have to use the moderate block size. You don't use much bigger block, because if you use bigger block, then the complexity is very hard, but the performance also decreases. So you have to moderately use. So you can use 64-bit block as an ideal. And the key size can be 128 bits or 56 bytes, anything you can use. So that also the same way, if you increase the key size, it becomes more complex, it increases the complexity, but it will decrease the performance also. You have to moderately use the key size. For DS we use the 56 bits key size. Number of rounds, so you can also vary the number of rounds for different algorithms. It is not compulsory that you have to use these number of rounds. The number you increase, the number of rounds you increase, the complexity increases even more. Okay, usually 16 rounds are used. And round function, as we have discussed in the previous slide, a round function is a function generated from the right hand part data, taking the output of the right hand part and also from the sub key. So both the combination you generate a round function. You can see fast software encryption or decryption. So we have to use the software like it has to be encrypted and decrypted very fastly. You shouldn't wait for a long time for encryption, you shouldn't wait for a long time for a decryption, because if you select a block size or key size very huge, your software will get down. So that's the reason why you have to select the moderate block size and moderate key size, and also the moderate number of rounds. And ease of analysis, here the algorithm which you have chosen should be very easy to analyze the complexity of the ciphertext. So the analysis process should be very easy. So these are the Feistel cipher design elements. These are the design elements which you frequently use in the Feistel cipher. Now let us see Feistel cipher decryption. As we discussed earlier, it is a inversible function. Feistel cipher structure is an inversible substitution and permutation network. In the same way, that means that you don't need to use a separate algorithm for encryption and separate algorithm for decryption. You can use the same algorithm for encryption and both decryption also. And what you will do is, I explain this one, you will get the ciphertext here. Here you take the ciphertext as an input in decryption. Okay, for decrypting the ciphertext to recover the plain text, first you have to use the ciphertext as an input and process the algorithm in a reverse order. That means you have to use the K16 in the first round. See, this is LD0 and RD0, left hand decryption 0 and right hand decryption 0, and use the function basing on the K16, not with the K0, not with the K1. K16 you have to generate a F1 round function and do the exclusive OR. This LD0 is equal to RD16 of the encryption process. If you see, the LD0 is equal to the RE16 and RD16 is equal to LE16. Sorry, RD0 is equal to LE16. So completely reverse. So you have to start from the reverse and do the same process what you do in the encryption, and finally you get LD16 and RD16, that is left hand decryption round 16, right hand decryption round 16, and you will swap those data and you will get the original plain text which you have used for encryption. So this is the process of this Firestone cipher decryption. So now let us see the data encryption standard. In short, it is called DES. So it is one of the most popular algorithm for the data encryption. So it is also very important in exam point of view. You could almost get this question in your final examinations. And regarding to this data encryption standard, this encryption standard uses the concept Firestone, which we discussed recently. So DS uses the Firestone cipher structure, and this is adopted in the year 1977 by NBS, that is National Bureau of Standards. Now it is National Institute of Standards. So under the project of FIPS, Federal Information Processing System 46. So they adopted, and this is actually done by IBM company, and this is adopted by the National Bureau of Standard. So this DES uses a 64-bit block. As I said earlier, you can use 128 bits or 256 bits, whatever the bit block you can use, but in DES we use a 64-bit block for the input and uses the 56-bit key, and the key size is the 56 bits, and it has a widespread use. So it is widely used in many applications and many countries, but still it is having a controversy over its security. Given it is having a wide popularity, it is having some controversial regarding its security. Now let us see the DS history. So how the DS is developed. So let us see. So it is developed by the IBM company under the project Lucifer Cipher. So they developed a algorithm called the Lucifer Cipher, so which is led by the team Firestone in late 1960s. So under the guidance of the Firestone, they developed Lucifer Cipher. It uses 64-bit data blocks with 128-bit key. So they used the bit data block 64 bits only, but the key size is 128 bits. They redeveloped this project. So initially this project was prepared for one client. So they developed the Lucifer cipher for one of the client in London, but it becomes very popular because of its success. They redeveloped for the commercial cipher. with input from NSA, because NSA asks for the standardizations, any algorithm, so they redeveloped because of that purpose. In 1973, National Bureau of Standards issues a request for proposals for National Cipher Standard. So National Bureau of Standards, they proposes from different companies the Cipher Standard, the National Cipher Standard, and in that proposal the IBM submitted this revised Lucifer, and which was eventually named as the DES. So for the proposal the IBM submitted this revised Lucifer, and it is named DES. This is the history of the data encryption standard. Now let us see DES design controversy. So why data encryption standard becomes controversial? Because even DES is standard, the standard is publicly accepted, it was considerably controversy because about its design, because of the size of the key chosen. Because for Lucifer they had chosen 128 bits, and why they had chosen 56 bits for this project. So that is one controversy. And another controversy is the design criteria they classified. So the design criteria which they classified was not seeming that it allows a trapdoors to the security. So that is one problem. But even these problems are specified, it is publicly accepted. The subsequent events and the public analysis shows that it is publicly accepted. So it shows the design was appropriate. So DES was mainly used in financial applications, and it is still standardized for many legacy applications. That is in the sense, for many of the older applications, this is the standard still is using. So this is about the DES design controversy. Now let us see the DES encryption overview. So the procedure followed for the DES. So let us see initially the 64-bit block, the input bit block. So for this input bit block, the initial permutation is done. In the sense, so these 64-bit blocks are divided into two halves, and initial permutation is done. Here it is 2 blocks is not shown, so it is intense. So this 64-bit blocks has done initial permutation, which is not there in the Feistel cipher. So the difference between this DES and the Feistel is, here we use initial permutation and final permutation, which is not in the Feistel, and remaining things is almost similar to the Feistel. So initial permutation is done for these 64-bit blocks. This is the left hand part, and from the right hand part key is also generated, that is a 56-bit key, and for this 56-bit key is also the permutation choice 1, PC1 is generated, and this 56-bit key is, after doing permutation, it becomes 48 bits. The 56 bits become the 48 bits by doing some PC, and then the left circular shift. So after doing some left circular shift, the 56-bit output is given to the, once again permutation choice 2 is done, and the output becomes the 48 bits. This 58-bit input becomes a 48-bit key. This is the round key or the sub key. The key, after doing permutation, it becomes a 48 key, 48 length key, and it is given as input to the round function. This is the round 1. So from the left hand part, initial permutation is done, and you get the output 64 bits, and for this round function the key 48 bits is added, and you will get the output once again 64 bits. So in the same way, 16 rounds in the DES we use 16 rounds. The same process is repeated. So means for each round the left circular shift is done, and permutation choice is permutation choice 2 is done, and that 56 bits becomes the 48 bits, and that will be the sub key for each round. So after finishing all those 16 rounds, 32 bit swap is done, and then final permutation, which is the inverse of the initial permutation. So this initial permutation, this final permutation is simply the inverse of the initial permutation, and you will get the ciphertext. So this is the encryption process of the data encryption standard. Now here the round function is not clearly shown, means the internal details of the round function is not shown here in this diagram. This is a WAVR because it is a WAVR view of DES. So if you see the internal in-depth of the round function, you can clearly understand how the round function is generated. Now let us see what is an initial permutation. So this is the first step of the data computation. So in the DES algorithm, the first step of computation is the initial permutation. What this initial permutation will do is this will reorder the input data bits. Just do the permutation, reorders the input data bits in such a way that even bits to the left hand part and odd bits to the right hand part. This process is quite similar in many hardware and something. So it is simply nothing but it will do the permutation of those 64 bits input block. 32 bits to the right part, even 32 bits to the right part, and so left part, and odd 32 bits to the right part. So this is the initial permutation. And now let us see the DS round structure. So how the round function will be generated. So initially the 32 bit left part and the right parts, the 64 bits is divided into two equal parts, that is 32 bit left part and 32 bit right halves. So just like Feistel cipher, Li is equal to Ri minus 1, that is left part. For example, consider I is 0, I is 1. So left part 1 is equal to R1 minus 1, in the sense R0. So L1 is equal to R0, that is round function 0 is directly swapped to the L1. So right part of first round becomes the left part of the second round. So that's L0, L1 becomes the, R0 becomes the L1. And if you see Ri, so for example, consider it is a I is equal to 1, that is round left part 1, right part 1, that is the second round right part. So how that becomes is left part 0, that is 1 minus 1 is left part 0 is exclusive OR with the function. And how the function is generated is, how the function is calculated is right part of 0 comma round function k0. So with the combination of the sub key and the right part R0, the function is calculated, and that is exclusive OR with the left part, and that becomes the R1. So L0 becomes the R1. So what F takes is 32 bit right half and 48 bit sub key. What this round function takes is the 32 bit the right half. From right half it takes 32 bit and also 48 bit sub key. Expands R to 48 bits using permutation expansion. So the right part, so it expands the right part to 48 bits, because actually the right part is only 32 bits, left part 32, right part 32. What it does is right part it expands. So you can understand clearly if you see the, so the round function diagram is not there in this slides if you have, so I will place it, I will add it later. So this is how the right part is expanded, the 32-bit right part is expanded to 48-bit using expansion permutation, and add subkey using exclusive OR and subkey, because why it is expanded to 48-bit is key is 48 and R part, right part should also become 48. Only then if these two are equal bits, then you can generate function. So right part is 32, that's why it is expanded to 48. So 48 and key is 48, then it is easy for making 48. So that's why right part is expanded, adds subkey using exclusive OR, and passes through 8 S boxes to get 32-bit per. So this whole function output passes through the substitution box. So input is 48 bits, but you should get the output 32 bits. So that 48 bits is divided into 8 parts with 6 inputs in each block. 6 into 8 is 48. So for each block you get 6 bits. So the output is 32 bits. How you get 32 bits? Each 6 bit becomes the 4 bits. So 4 into 6 is equal to 32. So once again the substitution is done in the S box. You can see the diagram here, how the 48 bits becomes a 32 bits. I will explain it. So it passes through the S boxes to get 32 bits and finally permutates 32-bit permutation. And finally once again permutation is done for these 32 bits and gets the output 32 bits only. See here, the right side part 32 bits, the function is calculated. Okay, so for these 48 bits it is divided into 8 substitution blocks. In the S box, these 48 bits is divided into 8 boxes. So in each blocks, if you see 6 inputs, and each block generates 4 outputs. So 2 inputs will be cancelled. After doing some substitution, you get only 4 outputs for each block. So 4 into 8 is equal to 32 bits. This is how the substitution box will do. So substitution boxes. So theoretically it is written 8 S boxes which have 6 to 4 bits. Each S box is actually 4 little 4-bit boxes. So the internal description, if you see, each X box is having the 6 bits. Among those 6 bits, first bit and the 6th bit are the row bits, and select one of 4 and select one row of 4. Okay, among the 6 bits, first and 6 are the row bits, and inner bits 2 to 5, 2, 3, 4 and 5, those 4 bits are the column bits. These are 1 and 6 are the row bits and 2 to 5 are the column bits. And for the output, one of the 1 and 6 becomes a row bit and remaining 3 becomes a column bits. So result is 8 lots of 4 bits or 32 bits. The row selection depends on both data and key. So the row selection, how you will select a row, that becomes on the data part of the right part and also on the key. Now let us see DES key schedule, how the key is generated for the data encryption standard. So subkey is used in each round. If you see, the subkey is used in each round from K0 to K15, 16 rounds used. So initial permutation of the key, permutation choice 1, it selects 56 bits into two 28-bit halves. So initial permutation, that is the permutation choice 1. So for the key also, key part also, the initial permutation is done. Just like the data part, how the initial permutation is done, for the key part also initial permutation is done. and that initial permutation is called the permutation choice 1. So this 56 bits is divided into 28 bit halves, and this is done for 16 stages. For each round the same process is done, and in each stage each half rotates separately either 1 or 2 places. So each 28 bits rotates separately either 1 or 2 places. Depending on the key rotation schedule key, they selects 24 bits from each half. So after rotating, they generated 24 bits. That means from 28 bits they generate 24 bits from each half. So from first half they generate 24 bits, and the second half they generate 24 bits, and the total becomes the 48. So that's the reason why subkey is having 48 bits. Usually the key is having 56 bits, and after doing permutation choice 1 they becomes the 48 bits. This is about the DS key schedule, and let us see how the decryption is done in the data encryption standard. So decryption is just a reverse to the encryption standard. Okay, just like Feastel design, decryption steps is a reverse to an encryption. So in this, what is done is subkeys in reverse order. You will use the subkeys in reverse order. That is, in encryption you use the subkey 1 first in the first round, subkey 2 in the second round, subkey 3 in the third round, and so on. For the last round use the subkey 16. But whereas in the decryption, in the first round of decryption use the subkey 16, and in the second round of decryption use the subkey 15, and the same process repeats, and in the last round use the subkey 1. So after generating the subkey 1 you will get the plain text. Okay, so initial permutation undoes the final permutation step of encryption. First round with SK16 undoes 16th encryption round. So this is how the decryption of data encryption standard will be done. And now let us see avalanche effect. So avalanche effect is a sense, it is a property of the encryption algorithm. It is one of the property of a which is desirable. Okay, so this is the property which is desirable in encryption algorithm. If this property is there, you can say this is a complex encryption. So what this avalanche effect is, change in one input or key bit results in a change in approximately half output bits. If you change just one input bit in a plain text or in a key, after processing all the algorithm, the output should be like half of the output bit should be changed. Just by changing one bit of input, the half of the output should be changed. So if it does like that, if that is changed like that, then you can say it is avalanche effect. So you can make attempts to home in by guessing keys impossible. So in the sense, so if you try to do attempts on the ciphertext, it should become impossible to generate a key. So DS exhibits strong avalanche. So we can clearly say data encryption standard exhibits a very strong avalanche because of doing a lot of substitutions and permutations in the algorithm. So it exhibits a strong avalanche. Now let us see the strength of DES, how strong it is from cryptanalysis. 56-bit key, it uses the 56-bit key. So the security is 2 power 56, that is 7.2 into 10 power 16 values. So the cryptanalyst has to generate 10 power 16 values, which is very hard and which is very complex. Brute force such is not at all possible, but the recent advances shown that in 1997 on internet in a few months, so they gained an attack just within a few months. They gained the internet, which uses the DES, and in 1998 also they succeeded in a dedicated hardware EFF in a few days, electronic frontier. So electronic frontier succeeded in affecting the hardware, and in 99 above combined in 22 hours. So both the internet and dedicated hardware, they succeeded within 24 hours, but still must be able to recognize plain text. So that's the reason why now they are searching for the alternatives for the DES, and they've introduced triple DES, advanced ES, so AES, that is advanced encryption standard. So even it is very stronger, they are recently cryptanalyzed. This DES algorithm is cryptanalyzed in those years in 1999 and 1998. So that's the reason why some more similar type of but very complex than the DES, called the AES, advanced encryption standard, and triple DES are invented. So